Raw data is chaotic. To make it useful at scale, systems must organize that data into rigid, predictable frameworks. In 2026, a specific nomenclature, Tribe v2, emerged simultaneously across 4 separate high-technology sectors. Researchers at Meta released a foundation model for computational neuroscience under that name. At the same time, molecular biologists adopted a technique called hypertribe for RNA editing. Concurrently, a popular SaaS community platform rebranded its second-generation architecture as BetterMode v2, and the decentralized finance sector reeled from the legal fallout of the Tribe DAO v2 crisis. This shared naming convention points to a verifiable symptom of what we call architectural convergence. Across these sectors, the shift from version 1 to version 2 highlights a consistent technical trajectory, the movement away from experimental, single-purpose tools toward rigid, scalable infrastructure. A mature V2 architecture is defined by 3 objective pillars: generalization, integration, and resilience. By analyzing these cross-disciplinary patterns, we can map the universal engineering principles that dictate how the next generation of human-aware technology is built. The first pillar is generalization. At Meta's fundamental AI research team, engineers set out to build an in silico digital twin of the human brain, a computational model capable of simulating fMRI experiments in seconds. They based their work on the representational alignment hypothesis. This principle dictates that deep artificial neural networks and biological brains compress the statistical regularities of the physical world using highly similar geometric patterns. Their first attempt, Tribe v1, required rigorous recalibration and was limited to analyzing just 4 specific subjects. Tribe v2 abandoned that specific calibration entirely. By using a training technique called subject dropout, the system learned to make zero-shot predictions for completely new individuals. This chart compares the capacities of the 2 models. The mapping resolution expands from a 1,000 voxel limit in version 1 to the 70,000 mark in version 2, covering both cortical and subcortical regions across 700 subjects. We see the exact same principle at work at the microscopic scale in molecular biology. The original Tribe RNA editing technique relied on a standard enzyme to identify target sites. That enzyme had a strong structural bias toward double-stranded RNA, which resulted in high false negative rates when analyzing transcript interactions. The V2 iteration, hypertribe, swaps that standard enzyme for a hyperactivating E488Q mutation. This specific architectural change removes the structural bias. By removing the bottleneck, hypertribe can map transcript interactions in a sample of just 100 cells. Previous gold standard methods required millions of cells to achieve similar results. Generalization is achieved by altering a system's core mechanics to remove biological or structural biases. This allows highly specific experimental tools to scale into universal foundation models. The second pillar requires managing structural friction. Biological blood-oxygen-brain signals are governed by the hemodynamic response function. When a person sees or hears something, the corresponding bold signal in the brain peaks roughly 5 seconds later. Engineers face a distinct tension here. Artificial perception processes data instantly, but biological reality is slow and noisy. This schematic illustrates the architecture Meta designed to solve temporal friction. Tribe v2 utilizes 3 specialized frozen foundation models to extract features. VJEPA2 Giant handles visual streams, Wave2Vec BERT processes auditory patterns, and Llama 3.2 3B provides semantic linguistic embeddings. Keeping encoders frozen prevents overfitting to noisy biological data. The outputs concatenate into a single massive data array, then funnel into a temporal transformer with a 100-second context window, allowing the architecture to capture that 5-second biological delay.
This demand for tight integration extends directly into enterprise software, specifically the evolution of the Tribe social platform into BetterMode v2. Market demands forced BetterMode to abandon isolated, single-function community tools. They implemented a modular block system, creating a multimodal hub that integrates live events, advanced polling, and AI-powered search. To support this, they rebuilt their infrastructure around a developer portal, equipped with a GraphQL API and webhooks. This synchronization layer automates logic between external applications and internal databases. Whether merging trimodal sensory inputs for a simulated brain or unifying software modules for an enterprise community, scaling requires a rigid integration layer to synthesize disparate data streams into one functional environment. The ultimate test of any integrated system is its capacity to absorb catastrophic stress. Without resilience, scaled architectures collapse. In 2021, the Fei protocol algorithmic stablecoin merged with the Rari Capital DAO. The resulting Tribe DAO was intended as a proof of concept for scaled, decentralized financial governance. In April 2022, the architecture faced a massive stress event when its Fuse money market was exploited for $80 million. This flowchart tracks the ensuing governance failure. 75% of token holders voted off-chain to fully reimburse the hack victims. However, that consensus was abruptly blocked by core insiders who used their structural veto power to prioritize treasury stability over the vote. The disconnect between community consensus and on-chain execution mechanics destroyed trust in the system, forcing the DAO to wind down its operations. By 2024, the failure of this digital architecture required physical legal intervention. The San Francisco Superior Court mandated recovery mechanisms for the investors. This table breaks down the resulting 2026 settlement. While stablecoin holders received a one-to-one redemption for DAI, the victims of the original hack received only partial capped payouts from the merger reserves, alongside a $17.8 million settlement fund for initial event participants. Compare this collapse to BetterMode's V2 resilience strategy. When faced with scaling pressure, they sunsetted their free tier to prioritize back-end database throughput and introduced strict official resource spaces to guarantee information integrity under high load. A generalized, highly integrated system holds no value if its governance and operational mechanics cannot withstand adversarial conditions. We are now seeing these digital architectures map directly onto physical hardware ecosystems designed for continuous sensing. Prominent industrial designers are currently developing specialized hardware interfaces intended to host these complex foundation models in real-world environments. Production capacity for trimodal capture devices is scaling aggressively. Meta plans to expand production of AI smart glasses to over 20 million units by 2026. Simultaneously, advanced wearables like the Pixel Watch 4 are capturing continuous physiological data through multi-path heart rate metrics. Feeding continuous visual, auditory, and physiological data directly into a 70,000 voxel, zero-shot model like Tribe V2 theoretically enables the real-time prediction of human cognitive and emotional responses to a user's environment. This capability pushes against the boundary of mental privacy. The gap between encoding, predicting a biological reaction to a stimulus, and decoding, surveilling a private inner thought, is narrowing. In just a few years, this architectural maturation has replaced months of molecular lab work with seconds of in silico simulation and upgraded fragmented software tools into robust enterprise foundations. When complex systems achieve generalization, integration, and resilience, they function as a foundational layer of infrastructure. These are the frameworks that will predict our biological responses and organize the social and financial structures we occupy.